energy and or from potential energy to kinetic energy. And you have to know some of the characteristics of this potential energy and kinetic energy. So one of them we have discussed in our last lesson is about the potential energy, the gravitational potential energy. It is independent of the direction you throw it, right? So whether you throw it upwards, downwards, as long as the initial velocity is the same, so the final gain in kinetic energy will be the same, right? Maybe the time
Okay.
is different, but will be the same. So we're going to look at another characteristic of this potential energy and kinetic energy. So you read this 5.4, quiz 5.4, and I will explain to you.
Uh, um, your face. Sorry.
Bob.
Bob of mass m drops from a tree limb at the same time that Esther, also of mass m, begins to descend down a frictionless slide. If both start at the same height above the ground, which of the following is true about their kinetic energies as they reach the ground? A. Bob's kinetic energy is greater than Esther's. B. Esther's kinetic energy is greater than Bob's. C. They have the same kinetic energy. D. The answer depends on the shape of the slides.
Okay, right. Now the answer is they both have the same kinetic energy. Okay. Now the reason is because they start from the same height. So they possess the same amount of gravitational potential energy. So both of them, when they reach the ground, they possess the same kinetic energy because the same amount of gravitational potential energy is converted to kinetic
Yep.
energy.
Okay.
And uh, this conversion is independent of the path taken. And probably this Bob, he jumps down from the tree and fell vertically downwards, whereas this Esther came down using the slide. So even though it's a longer journey, but both of them possess the same kinetic energy when they reach the ground, right? So
Yep.
independent of the path, and it is also independent of the shape of the slide, right? Okay, next one. This next one is, okay, you read this one first. 5.5 example.
A diver of mass m drops from a board 10 meters above the water surface as figured 5.17. Declare air resistant. Use conservation of mechanical energy to find his speed 5 meters above the water surface. Find his speed as he hits the water.
Okay, so we are going to use the principle of conservation of energy, or they call it work energy theorem, or some other name, right? Now, it can be summarized in equation form, like this. It can be summarized in equation form, and we are going to make use of this equation to solve the problem. Now, what is this equation all about? This one, right? KEI plus PEI equals to KEF plus PEF. Now, what they are trying to say on the left-hand side is the initial mechanical energy. That means the initial kinetic energy plus the initial potential energy. This will be equal to the final kinetic energy plus the final potential energy. So what they are saying is that there is a conservation of energy. The total energy before and the total energy after, they are the
Yep.
same. Okay, then probably what is not the same is the interchangeable between kinetic and potential energy. So we're going to make use of this equation. The total, the sum of the kinetic energy initially is equals to the sum of the mechanical energy after. Okay, so I copy down the equation that we are going to use here. Okay, so
Okay.
the initial kinetic energy, okay, a diver, sorry, of mass m drops from a board. So he is not jumping, you know. If he is jumping, then he possess some initial kinetic energy, but then he drops himself. So that means initially his velocity is zero. So velocity zero, so the initial kinetic energy is zero. I draw out to show that they correspond with one another. Okay, where is it? This one. So this kinetic energy, the initial kinetic energy is zero because the initial velocity is zero. The initial potential energy is this one, mg times the height, mg times the height, and the height is 10 meters. This is the zero level, the height is 10 meters. Finally, when he reached the midway, right, find the mechanical energy, find his speed when he's 5 meters above the water level. 5 meters above the water level means he is somewhere here, the midway, right? So the final kinetic energy after dropping 5 meters, we don't know. We don't know the velocity. But the potential energy after dropping 5 meters become mg multiplied by 5.
Okay.
Okay. So now I move this mg5 over to the other side of the equation. So it becomes mg10 minus mg5. And it is equals to half mv squared. Now what they're trying to say is that the change in potential energy from 10 meters above to 10 meters to 5 meters above the water level, this difference is the change in potential energy, or we can say the loss in potential energy. Now this loss in potential energy is translated into kinetic energy, right? That is how we look at it when you rearrange the equation. Initially the equation is like this, right? Total energy before equals to total energy after. When we rearrange the equation, it becomes something like this. So from this equation, we see that it is independent of the mass. The mass, you can cancel off, the m can cancel off. So when you cancel off all the m, the half v square is 10g minus 5g. Solving this equation, we have the final velocity 9.9 meter per second. Of course, you have to take square root and so on. This one, you know what to do because earlier on there's one problem like that. So you know what to do. Okay, now the second part of the question. Find his speed as he hits the water. So that means now he is at zero level, zero height. Okay, so what is his velocity? So again, we are using this equation, total mechanical energy, or the sum of the mechanical energy, initial mechanical energy is the same as the final sum of the mechanical energy. Mechanical energy is referring to both the KE and the PE. Okay, so now we replace the kinetic energy and potential energy by using their respective formula. Okay, so the first one will be the kinetic energy. So when he is at the top, the platform there, the velocity is 0. So the initial kinetic energy is 0. When he is at the top, the potential energy is mgy. In this case, y is 10 meters when he's at the top. Finally, when he reaches the bottom, we don't know what is the velocity. Never mind. But the kinetic energy is half mv squared. And also, when he reached the surface of the water, the potential energy is 0 because now he is at the 0 level. Again, the m can cancel off. The m can cancel off, and we have v square equals to this one. Half v square equals to 10g. When you move the 2 over to the other side, 2 times 10g, taking the square root, we have 14 meter per second, right? So all the time we are using the same conservation of energy equation all the time, right? Initial energy is the same as the final energy. The next question, qualitatively, how will the answers change if the diver takes a running dive off the end of the board? Okay, this is springboard. So in the first problem, he is not running. He is not running. So he has no kinetic energy, initial kinetic energy. But in question 5.5, he is running. So he possesses initial kinetic energy. Now, in the first question, which is this one, the initial kinetic energy is 0. The final potential energy is 0, right? But in the second case, when he is running, right? He's run, then he jumped from the board. Okay. Now, when he leaves the board, he has a certain amount of kinetic energy, right? The speed at which he leaves the board. So he has a certain amount of kinetic energy. Okay. So this will contribute towards the final kinetic energy. Because this one is 0, right? So this is the second case. First case, there's no kinetic energy, initial kinetic energy. Second case, there is initial kinetic energy. So this initial kinetic energy will cause the total or the sum of mechanical energy to increase. So when the total initial energy is more, so the final velocity will also be bigger. Okay, so answer is his final velocity will increase because he has initial kinetic energy. It is added to the total mechanical energy. I should be typing total mechanical energy he possesses initially. Okay, so this will be more accurate, right? So if he asks you what will happen to his final velocity will be greater, will be bigger. His final velocity will increase because in the second case he has initial kinetic energy. Any questions so far?